Thank you for the invitation. It's a great pleasure to speak at this occasion. And for me, I mean, personally, it was really the Orange book that got me interested in stable homotopy theory. So, well, thanks a lot for writing that, all the wonderful work that went into that. So yeah, I'm going to talk about a project with Thomas Schlank and Ed Stapleton. And this project starts with a very naive question, or maybe stupid questions. But let me start with something classical. So, we're interested in computing, say, unstable homotopy groups of spheres. And if you start getting into the subject, you look at the tables and you notice there's some sort of regular pattern there. So you see that if k gets larger and larger, it stabilizes. So that's the content of the Freudenthal suspension theorem. So really, it is a reasonable thing to consider the limit or the co-limit when k goes to infinity of these groups, and well, we call those the nth stable homotopy groups of spheres. And so I read this fantastic quote in Adams's book about early in the subject. Apparently, Eilenberg said that there are two cases one has to distinguish. So there is the stable case, and there is the interesting case. I'm not sure if this is still Anyway, so for the rest of this talk, I will assume that we are all interested in the stable homotopy groups of spheres. You may leave now if you like. So the first thing that we do is, when we study these groups, is we learn that we can look at them one prime at a time. So we may compute the stable homotopy groups of the p-local sphere spectrum, or maybe even p-complete sphere spectrum. And again, heuristics tell us that there are two cases to distinguish. There's some of the interesting case that happens when the prime is relatively small. So, TMF happens, and exotic elements in Picard group happen, and all these interesting things. And then there is a second part, which is somehow the generic part, when the prime gets very large. And maybe we consider those non-interesting. So the question that we would like to ask is very naively, so the question, how to make sense, how to interpret a limit over these groups when p goes to infinity. So of course, it's written, it doesn't really make sense because we don't have a system. There are no structure maps. So this is somehow really a naive question. But all of my talk is to somehow explain a mechanism or a framework in which one can make sense of that, plus that exhibits some interesting features of these limiting constructions. So what I would like to start with is actually a theorem that was very much the inspiration to our approach. And so this theorem has nothing to do with homotopy theory. So it really just somehow uses the same idea of a limiting construction. And I think it highlights some of the cool things that happen in these cases. So the theorem is the Ax-Kochen theorem. And it's from the 60s. And it says the following. So suppose that you have some positive integer. And there's a second condition, which I will fill in a moment. Then every polynomial over QP in at least d squared plus 1 variables which is homogeneous of degree d, homogeneous of degree d, has a non-trivial 0. So what I mean by that, of course you can take all the variables equal to 0, that gives you 0, but I'm claiming that in these cases there is a non trivial solution to the equation P equals 0. And this property is known as, you say that QP is a C2D field. So the D, well, this D and the 2 refers to the exponent here. So somehow it measures the deviation of QP, from being algebraically closed, maybe. You should think of this like that. So again, I'm not really interested in the statement of this result, but rather in the way it's proven. So let me sketch this proof. So the idea is to construct new fields So I'm going to construct those more carefully later on. Right now, I just want to highlight the properties they have and how to use them, and also the function field analog of those. So now, here's how you prove this result. So first of all, this result was known. The analog of this result was known in the function field case. So there's a theorem of Lang. That says that if you replace QP by its function field analog, then this guy is a C2D field for all P. So now, I fix one. So and then there's a second condition, which will be a condition on the prime. Which I will fill in a moment. Then, yeah, this holds. And second is the p-adic. Yeah. D squared plus 1. I mean, at least d squared plus 1 or more. But then, so that's a 0. That's d squared. So the first thing that they do is they lift this result to this limiting construction. So they show that this limit field is C2D, and this lift is known as something that's called a Wash's theorem, and that tells you that so what it says precisely in this case is that these guys have the C2D property if and only if these are C2D for almost all P. So we have it for all P, therefore we can deduce that these guys are C2D as well. Now, the second step is that they prove that in the limit, these two fields become isomorphic. So there's an isomorphism of fields like so. So in particular, you can immediately see that this guy is C2D. And then running this theorem backwards tells you that QP is a C2D field. But again, with this requirement, only for almost all P. So what happens here is that they construct these limiting fields, and not only do they see generic properties of all of this family of these families of fields, but also they become somehow they allow you to move information from characteristic P to characteristic 0. So this is somehow these are these amazing properties of these limiting constructions that we want to exploit. So then the condition here should be that so there exists some not natural number depending on D, and you want P to be greater than ND. So you have some finite set of exceptions. Okay. So our approach to the construction of these limits is somehow via categorification. So I mean, you know, we know that there's a nice category of spectra that encodes these stable homotopy groups of spheres, and similarly, we want to first build a category in which then we can interpret these limiting constructions. So, and I'm doing this in a somewhat more in a very general situation, but this generality makes the construction really, you know, very easy and very manageable. So compactifications in tensor triangular geometry. So the idea is to categorify. So let C be a symmetric monoidal stable category. And right now I'm being eclectic about what I mean by that. I mean, it could be triangulated, or it could be, you know, a stable model category or a stable infinity category. And I would also like to assume that it's compactly generated. So let's give some examples. So one example that is somewhat very well understood, and it's a good toy case to come back to, is the stable module category for a finite group. And K is a field, and maybe the order of G, the characteristic of K divides the order of G. So this category is constructed by taking the category of representations and modding out by the projectives. Another set of examples is the category of spectra, or maybe equivariant spectra, or maybe even some sort of motivic category. That's kind of the content of this conference. And the third example is maybe something like the derived category of quasi-coherent sheaves on some nice scheme. So I'm not going to really review this tensor triangular geometry in detail. I mean, it's a perspective that was developed by Balmer, but it's somehow very much in the spirit of chromatic homotopy theory. So if you read, for example, this Mike's announcement of the proof of the nilpotence theorem, I mean, somehow these ideas are already there in one form or another. So the picture you should have in mind is the following. So instead of thinking of this category C as an object, just as an object itself, really you can interpret it as a bundle that moves over a space. So there's a space. It's called the Balmer spectrum. And this category C should be viewed is some sort of sheaf or maybe pre-sheaf of categories over this space. And in particular, if you have a point in here, over this point, you can consider the stalk of this category. So this is somehow the local part of the category. So in chromatic homotopy theory, you might think the category is the category of spectra, and then the stalk at a single prime is the Kn local category. So this is the example you should have in mind. Say again? So the Verdier quotient would be corresponding to an open subset, and then so it would be something like the En local category, and then I'm looking at a closed subset of the open, so locally closed, and then I get like a formal completion. So this perspective allows you to somehow make like this previous naive question slightly more precise in the following sense. So now you can ask question 1. What is the limit of these stalks if p goes to infinity inside this space? So I have this p, I have this parameter p, I let it run inside the space, and I'm wondering what happens in the limit with these categories. That's the problem. So question 2, very good, is I'm phrasing it a bit more positively. I said, so maybe you can ask how to compactify C, or maybe at a boundary. So the idea here is you think of this space C, and somehow it's usually not compact. So maybe you can somehow compactify it, have a boundary, and then you could compactify the sheaf that lives over that, and just define the limit to be the stalk over one of these boundary points. So in this sense, this question 2 implies question 1, and this is the approach we will take. So, so the goal of this talk is to answer this in a specific case, or to study this in detail in a specific case. So study this when the underlying space is discrete. So this, at first this is a bit disappointing. You think maybe, well, you have a space, and now suddenly it's just a set. But at the end, in the second half, I will come to a very specific example, and you will see that this somehow simple situation leads to a very interesting theory, I think. But first, before we come to this special case of a discrete Balmer spectrum, let me just answer this question universally using the language of tensor triangular geometry. So first of all, if X is just a space, then we know how to compactify. I mean, there are many ways of compactifying, but in particular, we have this very nice Stone-Cech compactification. It has the universal property that if I have some compact Hausdorff space, Y, and the continuous map from X into Y, then there exists a unique map which is also continuous out of here, and this space, this Stone-Cech compactification, is itself a compact Hausdorff space. So now remember, so now we can apply this well-known pointed topology construction to the situation that we were in. So we have this category C living over X. So I'm taking the Balmer spectrum as my space X. I said it's a sheaf. So in particular, what does it mean to be a sheaf? Well, a sheaf, or even just a pre-sheaf, is nothing but a functor from open sets of X into categories. I have this map iota. So I can pre-compose, and I get a functor like this. I mean, it's a really, really simple, stupid construction. And I would like to propose to take this as a definition. So I would like to say that C hat is the compactification of C. So, okay, that's maybe a universal solution to the problem, but you can write down many universal constructions, and somehow you need to now start unpacking what's going on here. So this is something that you cannot directly work with. So what I'm going to do now is, as announced, I would like to restrict the kind of underlying spaces we have to discrete spaces and study this construction in a bit more detail. While I'm at it, I should say that so we also, in particular, we also have these stalks. So maybe study the stalks of this at some point in here. Okay, so let's assume that this X, I'm calling I from now on, is a discrete space. So the reason I would like to do this is because in this case, we have a very, very nice and clean model of the Stone-Cech compactification. So in this case, the Stone-Cech compactification is given as a set by all ultrafilters on I. So I'm going to define this in a moment. There's a second thing, there's also a topology on here. This is a topology, which I'm not going to review because it won't play much of a role. But there's a very nice way of making this into a compact Hausdorff space. So let me just give the definition of ultrafilter or remind you of what it is. And then use this definition to somehow give a more explicit model for this compactification or the stalks of this compactification. So here's a definition. So an ultrafilter on I is a collection of subsets of I it satisfies the following four conditions. The first one is a non-triviality condition, so it should not contain the empty set. Second one says it's closed under finite intersections. Third one is saying it's closed under supersets, so if A is an F, and A is contained in B, and B is also in F. And lastly, there's a maximality condition that says that any subset of I is either in F or its complement is. So I'm going to give an example in a little bit of this construction, of this definition, but right now you can just view this as a reminder of some points at topology. Okay. So here's the picture you should have in mind. So this I sits inside the Stone-Cech compactification in the following way. So you send an element of I to the following ultrafilter on I. You take all subsets of I which contain this chosen point little I. Okay, so that's, I mean, you can easily check that this satisfies this condition. And we call these specific ultrafilters, we call them principal. And then, potentially, there are more points in this compactification, and I'm just making a definition. I'm calling all the points that are not of this form, I'm calling them non-principal, and I say they give the boundary of the Stone-Cech compactification. In particular, these are these points that we add to the space at the boundary. So I started off by asking what is a limit, or what does it mean infinity? So now we have some notion of infinity, namely it's a point in this boundary. And there will be this boundary is non-empty if and only if the set I is finite. So in general, there will be many points in there. So now, with this definition, there's the following somehow crucial lemma. It says that, so we have this so we started off with this category C. Then we compactified it and we asked, well, so what is the stalk, the point? So now we have this model of the underlying compactification. So we take F in here and we ask, what does the stalk look like? And it's an easy computation that this thing is actually nothing but following categorical construction. So you take your ultrafilter, take an element in there, so that's a subset of I. You take a product of all elements in the subset U, and then take a filtered co-limit along the projection maps of these products. So that's a formula, and that is what I will denote by the following symbol, and it's called the ultra-product of the CIs. So we have an explicit categorical way of identifying these stocks, and moreover, we can interpret that in any category. So I started with the categories here, but I mean, of course, as long as you have products and filtered co-limits, you can make sense of this construction. This is what earlier we denoted by this limit, I going to infinity, maybe now along F of CI. Okay. So that is now a precise definition of what we mean by these limits. And now I would like to state, to connect up to this example from the beginning, I would like to make a precise statement of this wash theorem that we mentioned earlier. It's as follows. So let us assume that we perform this construction in the category of sets. So working category of sets. So I is some indexing set. That we have some structures indexed by I. So by structures, I mean this in the logical sense. So this construction first appeared in mathematical logic. And when I say structures, I mean so these XIs are some sets that are models for some language. So for example, it could be, so the XIs, for example, could be a collection of fields or a collection of rings. And I take some first order statement for that language. Then this theorem that is due to a wash says the following: two statements are equivalent. So then phi holds for these structures xi for almost all I. Almost all I in I. If and only if phi holds for the ultra products of the xi for all points in the boundary. Okay, that I understand that this is a bit of a, it's not so easy to maybe process this directly. So, but what the statement says is that you can test whether a statement holds generically for a family of objects by checking it for these stalks on the boundary at all boundary points. So I would like to paraphrase this by saying that, the boundary controls generic properties of the interior. Properties so let me make an example of that. Do you have a question? Yeah. Yes. Exactly. Yes. So this will be what we, we will do this in a moment, the things coming up in chromatic homotopy theory. But it's exactly the point. So, but let me make this example first, and then, because it's just to fix ideas. I take the prime numbers, and I take these structures to be just fields, the FPs. Then I claim that an ultra filter F in this case can be interpreted as something like a maximal ideal in the product of the FPs, and the ultra product is the same as the quotient. So we have to distinguish again two cases, namely the principal case, the case where we take a point in the interior, and the non-principal case, things that sit at the boundary. So in the principal one, the maximal ideal is principal if it looks like this. So you take strings of numbers of elements in here, such that the L coordinate is 0. So you fix some L and you look at all strings such that only this single one is fixed to be 0. And of course this forms a maximal ideal. And you immediately see that in this case, the ultra product really gives nothing interesting. So you just quotient by everything except for the things in the L coordinate. So you just get back your field FL. But in the non-principal case, something really cool happens. So first of all, I claim that a maximal ideal is non-principal if it contains the direct sum of the FPs. So that's a bit of a check, but it's easy to verify. And the second claim is that in this case, if you construct the ultra product, you of course get again a field, but now it's actually of characteristic 0. So somehow at the boundary suddenly you see that you have characteristic 0 fields. And I would like to point out that there is no contradiction here, because being of characteristic 0, contradiction to this statement of Wash's, being of characteristic 0 is not a first order statement. A field is you can ask for things like, so the field property can be checked using using that theorem, but you cannot check if something is characteristic 0. It's not a first order statement. So exactly the fact that this requirement of being of first order allows this additional flexibility when you form these ultra products. Other questions about this? So I would now like to use this construction and specialize it to chromatic homotopy theory and study this idea of going towards the boundary there. So I think we are at 4. Okay, so what's the chromatic picture? I can now write this very quickly with the language we've set up. So I have the category of spectra, sits over its space, and then we know that by the classification of the subcategories, that this is nothing but the following objects. So you have the prime direction, and then you have the height direction. This is viewed as a poset. So these are the primes. Over each prime, there is some infinite family interpolating between characteristic 0 and characteristic p. And we just have the quotient by this because height 0 does not distinguish between different primes. Okay. So in here, we have a nice subset, namely where we just fix a natural number n. So note that in particular, this is now discrete. And over here, what corresponds to this, this discrete subset should be some sort of sheaf, but it's discrete. So a discrete sheaf, I mean a sheaf on a discrete space is not so interesting. So this will just be a disjoint union indexed by the primes of some categories. And it's precisely as mentioned before, the Kn local categories. So these are here the Morava K theories. So, you mean here? Yeah, exactly. I mean, you can. I mean, I have not talked about topology at all, but you should topologize it. Yes. Yes. I mean, it's like the opposite of Zariski topology, right? I mean, I think that Ballmer somehow turns it around. I mean, like if you take the thing corresponding to NP and take its closure, then it's all the you want it to consist of all the thick subcategories that are contained in that. So it closes it upwards. It's kind of reversed. So I'm only going to consider this subset, and that is in order to somehow just have a discrete part. I mean, you could also take different slices, but I do not want to go into the upwards direction. And the theory already tells you, we had this categorical formula for what these stalks look like, and I want to work now towards giving a nicer model for these stalks. And that's related to another classical question in homotopy theory. I want to quickly review. I'll call this approximations. I mean, I'm reviewing this. I guess most of you are familiar with that, but I think it's a nice way of organizing your thoughts. So let's start with the simplest example, just looking at bottom piece, just looking at K0 local part. So that's just rational spectra, and we have a functor taking Q homology with Q coefficients that goes to graded rational vector spaces, and we all know that in this case this is an equivalence. So in particular, you know, that this category is completely algebraic. We completely understand this category. So now you can ask the same question about what happens at infinity. So you can ask, how do we understand this category? So this is nothing but the p-complete category. And again, we have a nice functor, just taking homology with fp coefficients. But of course, it's very far from being an equivalence. So the first thing that people then tried is, and there's this idea of Adams's, that, well, you have to be, I think, I don't know, I mean, might be other people as well, but so you really want to enrich your situation. You really want to also consider the co-operations here. So there's a forgetful functor from co-modules, maybe graded co-modules, over the dual standard algebra. And these cooperations act naturally on the homology of any space. So in other words, you have a nice factorization like so. And you would like to ask, well, so how good of an approximation is this category, the p-complete category? And Adams answers this in the following way. He says, well, you know, you can kind of go back using the Adams spectral sequence. So it starts with an object in here, I mean, the homology of some space or spectrum, then takes only information in this category and tries to converge to the homotopy groups of the p-completion of that spectrum. But of course we know that this spectral sequence is very complicated. There are many differentials. So this approximation, so somehow this measures that this approximation is very coarse. So now we have these two extreme cases. So one where the approximation worked very well, one where, you know, it was pretty complicated, pretty far away. And now we ask what happens at the intermediate layers. So in this case, one can set up a completely analogous story. So, and I'm now making, I should make a disclaimer, I'm now making a silent switch from the Kn local category to the En local category. I can, so the results that we are going to prove in the end are also true, can be modified to be true as well for the Kn local category, but the statement is slightly simpler for the En local category, so I'm going to work with that. So instead of taking mod P homology, we now take homology with respect to this Morava E theory, and luckily Vesna already introduced it. So this is Morava E theory, height n and prime p, and implicit or, you know, some perfect field and the formal group of height n over that. And I'm going to be sloppy and just denote it by E. Then we have an analog of this dual Steenard algebra, which is slightly more complicated. It's again given by the co-operations, but now it doesn't form a Hopf algebra, now it's a Hopf algebroid. And associated to this is a category of comodules, or graded comodules. and again a spectral sequence, an Adams type spectral sequence. It looks like this. That's the E2 term. And it tries to compute Gauss field localization of the spectrum X. So we've seen this all before. And again, the question is, how good of an approximation is that? So in other words, this spectral sequence really measures how far away this category of cool modules is from this E-local category. So and there's a wonderful theorem that answers that question, at least for finite spectra, say. That's due to Hopkins and guess who? And that's the following. And so somehow this theorem, I think, is it was mentioned before. This is somehow at the heart of chromatic homotopy theory. It tells you that you can understand these intermediate layers. In principle, you can understand them in finite time. So here's the statement. So let's say, for simplicity, just a sphere. Then the spectral sequence over there, the spectral sequence has a horizontal vanishing line. At some ER page. So at some point you run some differentials, and then at the finite page there's a horizontal vanishing line. Moreover, if the prime is very large, and you can quantify this, then it collapses even at E2. So this is what I would consider to be the generic part, and this is also what we are trying to capture in this approach. So, in other words, the way to think of this theorem is to tell you that, these categories of cool modules are very good approximations to homotopy theory, and the larger the prime, the better they approximate homotopy theory, E-local homotopy theory. So people then tried to make this, take this statement, this theorem, and actually turn it into an equivalence of categories, or say something about, make a precise statement about how good of an approximation this is. So another theorem, and it very much relies on work of Gauss fields at height 1 that I think predates many of these developments, and then it appears in unpublished work of Jens Franke. That's the following remarkable statement. So he says, well, okay, so we would like to understand this E-local category. So maybe now let me add N and P again. And we would like to approximate this with this category of cool modules. So if I want an equivalence of categories, I mean, I have no hope for that to be true, because, well, after all, this category is triangulated. This category is abelian. So this doesn't quite, there can't be any equivalence of categories. So the first thing that you might want to try is to derive this category. So it's a Grothendieck abelian category, you have a knife derived category, and now you can ask, is this category equivalent to that? Well, again, this cannot be true, because in here, remember, we had graded cool modules, so now you suddenly have two ways of moving things around. You have an internal degree, and you have a homological degree. So then Franke had this idea of periodizing this category. So now his result is as follows. So he was saying that you want to make a statement that not just captures a triangulated structure, but maybe even the homotopy theory. So he was considering the derivator of these categories, and derivator of this category. And then his result was as follows. He said, well, there are functors, and the two functors converge if p goes to infinity. So what do I mean by that? So convergence of derivators means that, so derivator is something which you can evaluate on a diagram. And what he's observing is that if the diagram, so the diagram has some dimension, you can take its, you can take its nerve, it has a dimension, and he says that if p gets larger and larger, this becomes an equivalence on larger and larger diagrams. So in other words, in the limit, the entire homotopy theory of the EN local category is captured by this algebraic category. So this would be a super clean solution to this problem of how good you can approximate homotopy by algebra if there wasn't a problem. So the problem is that this, unfortunately, yeah? Yes. Yeah, it's quadratic in P. But the problem is that it is not, because so it's actually not a theorem, it's a claim. And that was noticed by Irakli Pachkoria. So the problem is that so Franke writes down in a very ingenious way comparison factors between these two derivators, but basically by unwinding the construction of the atom spectral sequence. And this construction is just so complicated that it seems like his proof that these functors are even exact is potentially false. So you can fix that at large primes and height 1. This is what Irakli did, but it appears to be extremely difficult to actually turn to correctly construct these functors. So this is very much an open problem, as far as I understand. It's also not published; it's a preprint from the early 90s. So now I would, with that in mind, I would like to combine all the things that try to explain, put them together. So, and that's what we call ultra-chromatic homotopy theory. So remember, so we had this discrete set. You fix some height and let the primes vary, and get this sheaf on this discrete space. And now I'm actually working with the EN local categories, not the KN local categories. And we said we can compactify that by taking the Stone-Cech compactification. That's just notation so far. And we said that we can furthermore understand what happens at a point. So we can consider the stalk of that compactification at F. And this was this ultra-product construction. Or in other words, what we at the very beginning called the limit, maybe. P going to infinity along that. And there are two cases to consider here. The first case is that what happens in the interior of this set. So what happens if I take a principal ultrafilter and compute these stalks? Well, as before, as we saw in this finite field example, it's very easy to see that the ultra product in this case gives you back something that you started with. Oops. And adjust the value at L of these categories. So now, of course, the question is what happens at the boundary? And I can now finally state our main theorem. That answers that question. So now let's take a point in the boundary. And there exists a canonical equivalence of this stock with the analogous construction on the algebraic side of these categories that were considered by Franke. And this equivalence is a very good equivalence. It's an equivalence, in fact, of symmetric monoidal categories. Both sides are naturally Q-linear, which is somewhat surprising. And it also remembers all the homotopy theory. So what does this result say? Let me just try to put the pieces together. So first of all, so this category, well, let me make a zeroth remark. So first of all, I should say that this is not quite correct as stated. There is an additional finiteness hypothesis. That one should not worry too much about. So the first thing is that it answers this question how to take limits of homotopy groups when the prime becomes large. So the homotopy groups in this category naturally encode that. That's the first thing. Second thing is it solves this problem that that was there in Franke's theorem. So it actually tells you exactly that these indeed are the correct algebraic approximations that happened in the limit. But nicely, it avoids the construction of these functors at any finite prime. So this is very similar to what we saw in the Ax-Kochen theorem. In the Ax-Kochen theorem, you couldn't construct this isomorphism by writing down an isomorphism between QP and this function field analog. It makes no sense. The equivalence only exists after passing to infinity. And the same is true here. This equivalence that we get is not constructed at a finite prime and taking a limit. It only exists at infinity. So it's somehow maybe philosophically the correct approach. And the third thing is that this result really allows you to use a version of this Ax-Kochen theorem, of this Wash theorem that controls generic behavior in the interior by studying the boundary. So what I mean by that is you can now prove results about chromatic homotopy theory by first proving them in these categories algebraically, then passing to the ultra product, move over, and then get that they are true for almost all primes by descending. So there are various applications, but I guess I'm out of time, so I'll stop here. So thanks.